So the question is, a n cross n is a matrix with real entries such that for all x belong to Rn, x is an eigenvector of A. You have to prove that A is a scalar matrix. So to prove this, my first observation is that An has n linearly independent eigenvectors, because any column vector from Rn is an eigenvector, so it has n many linearly independent eigenvectors, which implies that A is diagonalizable. This is a well-known result. We can use it and also try to prove it. And another thing to observe is that A inverse also exists. Now my claim is that A has all same eigenvalues. So to prove it, we will assume the contrary. I'll assume that, let's say, lambda 1 and lambda 2 are two distinct eigenvalues of A. Implies A x1 equal to lambda 1 x1 and A x2 equal to lambda 2 x2, where x1 and x2 are two eigenvectors of lambda 1 and lambda 2 correspondingly. Since all the eigenvectors all the column vectors of Rn are eigenvectors, implies x1 plus x2 will be another eigenvector corresponding to some eigenvalue, let's say lambda 3, which implies that A x1 plus x2 equal to lambda 3 x1 plus x2. By doing some calculation, I can say that lambda 1 minus x3 times x1 plus lambda 2 minus x3 times x2 equal to 0, which implies that lambda 1 equal to lambda 2 equal to lambda 3. This is because x1 and x2 are corresponding to two distinct eigenvalues. That means that x1 and x2 are linearly independent. Now by definition of linearly independency, I can say that lambda 1 equal to lambda 2 equal to lambda 3. That means that every eigenvalues are same in that matrix. Now, since the matrix is diagonalizable, I'll use another result related to diagonalizability, which says that Am equal to the algebraic multiplicity of lambda equal to n, which is equal to the geometric multiplicity. Now, what is geometric multiplicity? Geometric multiplicity means the dimension of eigenspace related to lambda, corresponding to lambda, which is equal to n. Now, dimension of eigenspace, which is equal to the nullity of A minus lambda n, which is n. Now, if the nullity is n of some matrix, that means rank is 0. So here, the rank of A minus lambda I is 0, which implies that A equal to lambda I. Because if rank of some matrix is 0, which implies that that matrix must be 0 matrix. Therefore, A is a scalar matrix.